lecture. So as we left off last class session, we were discussing methods to prepare and synthesize ketones and aldehydes. And one method that we talked about last class session was the mercury catalyzed hydration of alkynes to give methyl ketones. Remember that mercury catalyzed hydration reactions follow Markovnikov regiochemistry, where water attacks at the most substituted position, and as a result, our ketone is installed at the most substituted carbon. Of course, since it's an alkyne, you'll always be able to get a ketone because an alkyne at maximum can have 2 carbons attached to it. Okay, so let's try to apply what we've learned last session, and let's refresh our understanding of the mechanism for mercury catalyzed hydration of alkenes by drawing out a mechanism for a mercury catalyzed hydration reaction and predicting the products from this reaction. So let's take about 3 to 4 minutes and let's try to draw out a mechanism for this reaction. You can share your responses in the chat or directly annotate your proposed mechanism on the class whiteboard. And if you have any questions as you work through this example, you can share your questions and responses in the chat or verbally, and I'd be happy to provide feedback and clarification. So let's work through this example for the next 3 to 4 minutes. And ideally, I'd like to see some students sharing their proposed responses, either in the chat or as annotations on the class whiteboard. So, does anyone have some initial inclinations? What do we think is going to happen in this case? What will our product look like?
Will the water first attack the carbon at the tertiary carbon?
So let's label them A and B. Which carbon will water attack?
B?
Yep, exactly right. So if we draw out our alkyne, so you can either draw the mercury coordination step as its own separate step. I like to draw it as water attacks the alkyne and then coordinates our mercury 2+. Okay, water adds following Markovnikov regio control. Okay. Now continuing our commentary, what will happen next? What's a reasonable proposal for our next step?
Will we have water attack hydrogen on the water that you added onto that?
So by attack, would it function as a base or a nucleophile? When you say attack hydrogen, what is it? What do we call that process when we pull off a hydrogen? It's like this is what you're referring to, right?
Yeah.
So what do we call this process when a base pulls off a proton?
Protonation?
Yep, or in this case, it would be deprotonation. So our alcohol in this case is deprotonated by our solvent, which is water. Perfect. So from here, we now have the following enol intermediate. And there are many ways to draw this second step. Would anyone like to propose what's going to happen next? Keeping in mind that this enol carbon is pretty electron rich. And remember, anyone can chime in verbally or in the chat. What will happen next? So we're almost there. We almost have a ketone-like functionality. However, we still have this mercury sitting around. So what would the next step be? If we want to eliminate off this carbon-mercury bond. The alkene will pick up a proton, okay? There are many ways to draw it, but the most direct would just be to directly protonate this alkene with an acid such as H3O plus that it's floating around in solution. Yep. Okay, we now get the following carbocationic intermediate. And now from here, how are we going to quench this carbocation? We have a carbon-mercury bond. Is there a way for us to eliminate this carbon-mercury bond? Can we eliminate off our carbon-mercury bond in this case? What do we think?
Yes.
Yeah, so just like a typical E1 elimination, our leaving group leaves and we eliminate to regenerate our alkene. Okay, so from here we now have a real and genuine enol. Okay, so how do we get our methyl ketone? So this enol form is not easily isolable. So how are we going to get our ketone? So we have an enol. Would anyone like to either draw or walk us through the steps to go from a enol to the ketone? So we have this enol, and in order for us to get to a ketone, in order for us to get to the ketone, which is our final product or the more stable form of this enol, inevitably what's going to happen? So we notice that we're going to have to lose a proton here, and we're going to have to pick up a proton on our alpha carbon. So can we draw that out mechanistically? Would anyone like to try to annotate that mechanistically or explain verbally? How would we go from this enol to our ketone tautomer? So water would act as a proton shuttle, okay? And what am I going to deprotonate? Which proton am I going to remove? So what proton will water pull off in this case? The alcohol proton, okay, perfect. And which source of what is protonated in this case? What are we protonating in this shuttling process? The alpha carbon. Yep, the alpha carbon's electron rich. So just like before, we're going to protonate our enol alpha carbon. Note we drew this proton transfer as an inter rather than intramolecular process. And with that, we get our desired methyl ketone. Perfect. Does this mechanism make sense to everyone? Does this process make sense? How we can prepare methyl ketones from alkynes via mercury catalyzed hydration? Okay, so let's continue on now and let's do some examples relevant to planning a synthesis. So I'd like us to take a look at the following structures, and I'd like us to draw the alkyne used to generate the following ketone. So we're thinking about the synthesis of ketones from a retrosynthetic perspective. What alkyne can I use to make each of these ketones? And in this case, I will ask students to try to share their responses as pictures or using the annotate tool. You could also state the name of these compounds. That's also an acceptable way to engage in this class-wide discussion. Um, but I would like to see some responses that have structural information. So let's try to think for a moment and propose what alkyne could we use to prepare each of the following ketones? So would anyone like to share a proposed precursor structure? What alkyne could we use to make any of these two ketones, A and B? And don't be shy to use the annotate tool to draw out your proposed response. You can annotate with your mouse or another writing implement through the Zoom annotate feature. So does anyone have a name or proposed structure? So we have, is this name for structure A or B? So we have a proposed precursor structure name of 4-methyl-pent 1-ine. Okay. 1, 2, 3, 4, 5, 4. So that would give us the following precursor structure. So we can derive this methyl ketone from the corresponding alkyne. 1, 2, 3, 4. Yep. So this structure of 4-methyl-pent-1-ine as a precursor for structure A looks perfectly reasonable. We have a student sharing a photo of their proposed responses in the chat. Give me one moment to take a look at that. Two things to note. With this synthetic process and this idea of retrosynthesis to prepare alkynes. And prepare ketones from alkynes. We can prepare any ketone or any methyl ketone from the corresponding terminal alkyne, because remember, water, our nucleophile in mercury catalyzed hydration, prefers to attack at the most substituted position. So we can readily prepare methyl ketones from the corresponding alkyne. We have another student sharing their proposed precursor structure for structure B. I also want to share that a student shared a photo of their response in the chat, and another student also came up with a very similar structure to prepare compound B. In both cases, this terminal alkyne, when subjected to mercury catalyzed hydration, will yield the corresponding methyl ketone. So let me clear those student annotations and let's redraw this structure just so that way it's a little bit larger and easier to read. Yep, so we have the two alkynes that we'd use to prepare each of these two ketones. Does this idea of retrosynthesis and planning a synthesis make sense to everyone? Do these examples make sense to everyone? Perfect. Perfect. So let's talk about an important complementary reaction to mercury catalyzed hydration of alkynes, which is hydroboration oxidation of alkynes. This is a useful method to prepare both aldehydes and the least substituted ketone. So borane adds to alkynes to give a vinylic borane. Oxidation with hydrogen peroxide produces an enol that converts to the ketone or aldehyde. What's really important is just like hydroboration of alkenes, hydroboration of alkynes favors anti-Markovnikov regiochemistry. So our borane is placed on the least substituted carbon. So hydroboration oxidation has the exact opposite regiochemical preference compared to oxymercuration or mercury catalyzed hydration. So hydroboration oxidation is a wonderful method to prepare the least substituted or least hindered ketone from an alkyne. And it's one of the few methods to directly prepare an aldehyde from an alkyne. Does that make sense to everyone? Okay, so let's keep going now. And just as a comparison, hydroboration oxidation converts terminal alkynes into aldehydes because the addition, well, the quote unquote addition of water, more correctly, the addition of borane, favors anti-Markovnikov regiochemistry. Now, just as a comparison, just to directly compare side by side mercury catalyzed hydration and hydroboration oxidation, the mercury catalyzed hydration favors Markovnikov regiochemistry, while hydroboration oxidation favors anti-Markovnikov regiochemistry. So mercury catalyzed hydration, useful to make ketones at the more substituted position. Hydroboration oxidation, one of the few methods to directly prepare aldehydes. Does everyone see the major difference in regiochemistry from these two synthetic methods? Okay. So let's take a moment and let's try to predict the product from the following reaction. And you can either provide the name or the structure of the product. So let's take about 2 to 3 minutes and let's try to predict the structure of the product from this hydroboration oxidation sequence. And don't be shy to share your responses as photos in the chat or directly as structures annotated on the class whiteboard. So hydroboration oxidation favors oxidation at the least substituted position, which in turn converts our alkyne into an aldehyde. Yep, so this proposed structure looks completely reasonable. So let's talk a little bit about how do we get this structure? Well, in hydroboration, addition of borane occurs to place the borane on the least substituted position. Boron is very sensitive to steric hindrance. From here, once we have our corresponding vinyl borane, it can be oxidized with hydrogen peroxide to yield the corresponding enol, which in turn can tautomerize to yield the corresponding ketone tautomer. In this case, rather than a ketone, we get an aldehyde. One, two, three, four, five. 1, 2, 3, 4, 5. It's always important to count your carbons just to make sure that your structure matches the carbon skeleton of your original molecule. Does this example make sense to everyone? Okay, so let's try another example. In this case, we're asked to provide the reagents needed to complete the following reaction. So we have two different reactions, and we want to fill in the blank with the reagents needed to complete this reaction. So we have two different alkynes, and in the first case, we're making an aldehyde. In the second case, we're making a ketone. So we'll call these two reactions A and B. And I would like students to share their proposed reaction conditions to complete reaction A and B. So we have a proposal for the first reaction. First, we have borane and THF, followed by hydrogen peroxide and sodium hydroxide. That's perfectly reasonable. Hydroboration oxidation favors oxidation and generation of a ketone or aldehyde at the least substituted position. And it's nice that I saw that the student noted in the chat you do hydroboration first, followed by oxidation. You don't just add all the reagents at once. It's a sequential process. Yep, so the conditions proposed for this first reaction are perfectly reasonable. We have multiple students commenting in the chat for the second reaction. We'd want to use mercury sulfate, sulfuric acid, and water. Yep, and you may also need to heat this reaction. Yep, those proposed conditions are perfectly reasonable, and they favor substitution and generation of a ketone at the most substituted position. Yep. In the case of oxymercuration, it is fine to add all the reagents at once because without the mercury, the hydration reaction is very inefficient. Does that make sense? Okay, so let's keep going then. And let's talk briefly about chemical tests and other methods to distinguish aldehydes from ketones. We actually employ many of these chemical tests in the laboratory as part of our identification and product characterization. One of the more common tests for an aldehyde functionality is the tolerance test. Aldehydes are readily oxidized by even mild oxidizing agents. In this case, silver ion serves as an oxidizing agent that is reduced by our aldehyde to silver metal. The silver metal precipitates and coats the container, producing a smooth, almost silver mirror-like effect. So the appearance and identification of this silver metal mirror-like appearance on the surface of your reaction flask is a definitive confirmation that you have an aldehyde. Ketones are not oxidized under these ambient conditions. Or to be perfectly clear here, silver is incapable of oxidizing a ketone under these Tollens test conditions. Does this make sense to everyone? The other oxygen comes from water in solution. So when we have water in solution, just like from previous mechanisms of aldehyde oxidation, you make the hydrate, and then silver is capable of facilitating oxidation of this aldehyde hydrate to the carboxylic acid. Does that make sense? Did that answer your question? So it's not quite an SN1 or SN2 reaction. The closest analogy for this mechanism would be we have coordination of our silver. And then from there, we lose an equivalent of hydride and silver is reduced. In this case, it wouldn't quite be appropriate to draw it just as like a 2-electron mechanism. This likely proceeds through a radical mechanism. But I want you to get this idea that in oxidation, water can serve as our ambient source of oxygen atoms, while the silver helps facilitate loss of a hydride equivalent. And that's why silver is reduced in this case. Did that answer your question? Perfect. Okay. So, on this note, let's talk about hydration and oxidation of aldehydes. Aldehyde oxidations occur through 1,1 diols known as hydrates. This occurs from a reversible addition of water to the carbonyl group. From there, the aldehyde hydrate is oxidized to a carboxylic acid by usual reagents that oxidize alcohols. So for example, once you have your hydrate, from there, just like any other alcohol oxidation that we've seen time and time again, we attack our electrophilic chromium atom. And then from there, water can pull off a hydride equivalent, and that generates our desired ketone. In this case, we regenerate our carbonyl that is part of our carboxylic acid. Now we still have our protonated carboxylic acid. So as a last cleanup step, we're just going to deprotonate our carbonyl oxygen. And that gives us our desired carboxylic acid from the aldehyde. So just to note, all aldehyde oxidations will typically go through the hydrate intermediate. The hydrate provides you your nucleophilic handle to attack your electrophilic oxidizing agent. And then from there, you can lose an equivalent of hydride and reduce your oxidizing agent down. Does that idea make sense? Any questions on this oxidation mechanism? Okay. So, unlike aldehydes, ketones typically require quite forcing conditions in order to oxidize a ketone. So, ketones undergo slow cleavage in the presence of hot alkaline permanganate. In this case, we are breaking the carbon-carbon bond. This is a useful method for cleaving symmetrical ketones, but these conditions are quite harsh. So generally, you're not going to oxidize a ketone under most conditions. It requires really quite forcing conditions to oxidize a ketone up to a carboxylic acid, as that oxidation requires breaking one or more carbon-carbon bonds. Does that idea make sense to everyone? Mechanistically, it's very different. We're not going to talk too much about this mechanism. This is mainly just to bring home this idea that it's very difficult to oxidize a ketone outside of forcing conditions. And it's only really useful for preparing symmetrical carboxylic acids and for cleaving symmetrical ketones. Does that answer your question? Perfect. So, what we're next going to talk about is this idea of nucleophilic addition reactions to aldehydes and ketones. We call these class of reactions 1,2 addition reactions. So aldehydes and ketones contain an electrophilic carbon that can be attacked by nucleophiles, right? The carbon associated with the carbonyl of your aldehyde and ketone is relatively electrophilic. As such, this carbonyl carbon can be attacked by nucleophiles. An addition of a nucleophile breaks the carbon-oxygen double bond and forms a carbon nucleophile bond, generating an sp3 center. Now, we know that the nucleophile typically approaches 75 degrees to the plane of your carbonyl carbon-oxygen double bond and adds directly to the electrophilic carbonyl carbon. For those who are wondering why this very specific angle, let me just draw out here a very important orbital. So this orbital is known as the pi star orbital. So our carbon-oxygen double bond is formed using our pi bonding molecular orbital. And for each bonding molecular orbital, we have a corresponding anti-bonding orbital. So just to help you visualize this, so we have our pi bond. This is the bonding interaction responsible for our double bond. And then we also have our anti-bonding orbital known as the pi star, which looks a little bit like this. Notice how there's no overlap between our two bonding atoms in our pi star orbital. And as we notice, if we look at this angle, if we take a look at this angle, it's about a 75-degree angle compared to our carbon-oxygen bond. Does everyone see how the nucleophile approaches and it attacks in a way to attack the pi star orbital? It approaches to attack that pi star orbital. Does everyone see how the angle of approach and the position of our pi star orbital match up almost exactly? And that is why we're breaking our carbon-oxygen double bond, because when you fill and you attack the pi star orbital, it breaks your bonding interaction. So rather than having a carbon-oxygen double bond, we're left with a carbon-oxygen single bond. So we make this tetrahedral alkoxide ion intermediate, and this alkoxide intermediate can be protonated or trapped with an electrophile. So this is a useful method to make substituted alkoxide intermediates, and you can even combine reaction steps together in sequence to do multiple reactions in a single reaction vessel. So in terms of the general mechanism, just to show this one more time, you have your aldehyde or ketone, essentially anything with a carbonyl. Your nucleophile adds into the carbonyl, breaking your carbon-oxygen double bond. From there, we now have a tetrahedral intermediate. And we get this product plus the other stereoisomer. Because note there are two faces for us to attack, so we can either attack from the top or the bottom face. So we get inherently two different tetrahedral intermediates. From there, the alkoxide intermediate can be either protonated or trapped. So if we want to protonate it, we treat it with H3O+. We protonate our alkoxide ion, and that in turn generates a highly substituted alcohol. Does this make sense to everyone? Does this mechanism make sense?
So when we are drawing that mechanism, it's important to note that it, like, where it's coming from, the nucleophile, or could you?
You can draw the approach from either face. There's no preference at this point for which approach is favored. And that's mainly a discussion for later classes in the upper division organic chemistry sequence. What I would note is that generally your nucleophile approaches to minimize steric hindrance whenever possible. Does that answer your question?
Yes, thank you.
Perfect. I mean, you can have some cases where if you have like a very set up substrate where one of the faces is preferentially blocked, then of course your nucleophile will prefer to attack from the least hindered face. So there are certainly substrates where there's inherent substrate bias, but for the most part, you get a mixture for most common substrates. Did that answer your question?
Yes, it did. Thank you.
Perfect. So let's talk about nucleophiles and just let's refresh our idea of nucleophiles. So nucleophiles can be negatively charged or neutral at the reaction site. And some common nucleophiles include water, alcohols, ammonia, amines, and some negatively charged nucleophiles that we'll see in the context of carbonyl chemistry are hydroxide, hydride, carbanions, such as Grignard reagents, alkoxide ions, and cyanide ions. And these are just some examples of neutral and negatively charged nucleophiles that we see in carbonyl chemistry and 1,2 addition chemistry. So, when we think about the relative reactivity of aldehydes and ketones, so let's just take a moment and let's consider and let's contrast a ketone to an aldehyde. Now, we know that in general, alkyl groups, are they donating or accepting groups? Are they electron donating or withdrawing groups? How would we describe these alkyl groups? Yep, they're sigma donors, right? So if we compare a ketone and an aldehyde, we can see immediately that ketones are stabilized by their electron donating alkyl groups. So if we had to compare, we would say that this aldehyde carbon is more electrophilic. So we can conclude that aldehydes have a more electrophilic carbonyl carbon. Further, if we think a little bit about steric hindrance for a moment, and we compare an aldehyde to a ketone, assuming these R groups are similar, these R groups take up space, right? So if we're a nucleophile that's trying to approach and attack an aldehyde versus a ketone, which of these substrates is less hindered? An aldehyde or a ketone?
Aldehyde.
Yep, aldehydes are less hindered, generally. So this combination of steric and electronic effects in turn means that in general, aldehydes are more reactive to 1,2 addition compared to ketones. So for example, if you have a substrate, let's just use an example where you have an aldehyde on one side, a ketone on the other, and you treat with sodium cyanide, one equivalent. Where will the cyanide anion preferentially attack? If there's a choice in the matter, where would it attack?
Where the aldehyde's located?
Yep, exactly right. The aldehyde, it's less hindered, it's more electron deficient. So as a result, you will see preferential reaction for the aldehyde in the event that you can equilibrate and in the event that the addition is reversible. You see preference for the aldehyde for non-reversible reactions, though in that case you may get a mixture. So addition into the aldehyde, carbonyl carbon would be our major product. And that's the same way, for example, if you have an aldehyde and a ketone, you don't have to worry as much about chemoselectivity if you treat this with, for example, boryl hydride, one equivalent. Which of these two carbonyls will be preferentially reduced? Where will hydride preferentially attack? Same idea. The aldehyde as well, right? So this applies both to nucleophilic additions in the context of formal 1,2 addition and also nucleophilic addition of hydride in the context of reduction. you can selectively reduce an aldehyde in the presence of a ketone. Does that make sense?
What is the meaning of the one equivalent again?
That we just use that there's a 1-to-1 molar ratio of hydride to our substrate.
Oh, okay.
Because if we used an excess, we would eventually reduce the ketone. Does that make sense?
Yes. Thank you.
Perfect. Okay, so let's take a look at nucleophilic addition reactions. So we concluded generally that aldehydes are generally more reactive than ketones in nucleophilic addition reactions. Further, we know that aldehydes are generally more electron deficient compared to ketones. Further, the transition state for addition is less crowded and lower in energy for an aldehyde because aldehydes only have one large substituent while ketones have two. So we can see visibly when our nucleophile approaches, when we have an aldehyde, the reaction site is a little less hindered compared to if we have a ketone. Do these points make sense to everyone? Does everyone see why there's a preference for nucleophiles to add and react with the aldehyde over the ketone? Perfect. So, just to refresh our idea and to really focus in on this idea of the electronic character of aldehydes versus ketones, generally the aldehyde carbonyl is more polarized than a ketone carbonyl. Generally, because the ketone has more alkyl groups, they can readily stabilize the carbonyl carbon inductively. Aldehydes experience less inductive stabilization, so they're much more reactive. It's important whenever you look at a new carbonyl functional group or a new functional group in general, you get a sense of its electronic characteristics. How electron rich is it? How electron deficient is it? As that will often dictate the relative reactivity in carbonyl substitution and carbonyl 1,2 addition reactions. Any questions on this idea? Okay, so let's talk a little bit about what happens when you start to deal with aromatic or conjugated aldehydes. So aromatic aldehydes are generally less reactive in nucleophilic addition reactions. The reason for that is there's an electron donating effect via resonance, as our aromatic ring can donate electron density into our aldehyde carbonyl. Further, we're able to more readily stabilize the built up partial positive charge on our carbonyl carbon via delocalization via resonance. If you compare the electron density maps for formaldehyde to, for example, benzaldehyde, you can notice very clearly in this electron density map that in formaldehyde, we have a relatively electron deficient carbonyl carbon, while the carbonyl carbon in benzaldehyde is relatively, and this is relatively, mind you, electron rich. And that is due to donation of electron density from our aromatic ring into our carbonyl carbon. Does this make sense? So formaldehyde is more reactive while the benzaldehyde aldehyde is less reactive because it's more electron rich. So generally aromatic aldehydes are less reactive. Does that answer your question? Does that make sense? Perfect. Okay, so our first textbook nucleophilic addition that we've seen and we've actually drawn the mechanism for in the context of oxidation of aldehydes is hydration, which involves the nucleophilic addition of water. So aldehydes and ketones react with water to yield 1,1 diols. This hydration is reversible, and a CHEM diol can easily eliminate water. So I want you just to note, the hydrate is generally not isolable for most of these aldehydes and ketones. Generally, the ketone or aldehyde form is preferred. The equilibrium massively favors the parent ketone or aldehyde. So just to draw up the mechanism for this reaction. So under ambient conditions, so under neutral conditions, we just see addition of water. We make an alkoxide ion, which isn't ideal, but it's palatable. And from there, we have a series of proton transfers where we protonate the alkoxide and we pull off a proton from our water adduct. And that in turn gives us our desired 1,1 hydrate. So this is the mechanism for neutral and basic conditions. Under acidic conditions, things change slightly. So let's look at the mechanism for an aldehyde, just for variation. The mechanism fundamentally is the same, whether you have an aldehyde or a ketone. The key difference under acidic conditions is we don't exactly have the strongest nucleophile imaginable. So in order to activate our carbonyl for addition, we are going to protonate our carbonyl. We now have a much more reactive carbonyl that can be attacked by a weaker nucleophile that would be found under acidic conditions. From there, that gives us our water adduct. And then from there, that gives us our desired hydrate product. Does this make sense? Okay, perfect. So let's reemphasize and review the two major ways that we can add water into carbonyls. So the addition of water can be catalyzed by both acid and base. In base catalyzed hydration, the nucleophile is the hydroxide ion. So in this case, hydroxide adds in to our carbonyl carbon. We in turn generate an alkoxide intermediate, which is in turn immediately protonated with water to make our hydrate. Does this base catalyzed addition of water mechanism make sense? Does this mechanism for hydrate formation under basic conditions make sense to everyone? Any questions? Okay, so let's look and let's talk a little bit about two other main features. Hydration is reversible, and a CHEM diol can easily eliminate water. So let's draw that out. So we have this wonderful CHEM diol. Well, we can just as easily kick out water or hydroxide via deprotonation. We go back to our alkoxide intermediate. And if we're under basic conditions, it's not unreasonable to kick out hydroxide. I can't imagine protonating to activate hydroxide as a leaving group would be viable under basic conditions. And from there, after kicking out hydroxide, we regenerate our parent ketone or aldehyde. So it's important to note that hydration is reversible and the equilibrium generally favors the ketone or aldehyde. Does that make sense? Okay, one other thing to note, this mechanism also applies to other nucleophiles under basic conditions. So for example, if you have an aldehyde and you treat it with a thiol, for example, like sodium thiophenolate. In this case, our nucleophile adds into our electrophilic carbonyl carbon. We make an alkoxide ion intermediate, and then we can protonate our alkoxide ion with water or another solvent component. Probably would be most accurate to draw it as protonating it using our parent thiol, just because we likely won't have water in solution in this case. Either way, we're able to generate our desired adduct. So does everyone see how this general 1,2 addition mechanism under basic conditions also applies to other nucleophiles under basic conditions? Okay, perfect. So let's look at the acid catalyzed addition mechanism now. So in this case, because under acidic conditions, we generally have weaker nucleophiles, we have to first activate our carbonyl via protonation. From there, we have a much more activated electrophilic carbonyl carbon that can be readily attacked with water. After a final proton transfer, we then get our desired hydrate. Does this acid catalyzed mechanism make sense to everyone? Any questions on this? Okay. So when we talk about all of these 1,2 additions under acidic conditions, generally addition of HY, where Y is an oxygen, halogen, or sulfur atom, gives an addition product. However, this addition product and the formation of this addition product is readily reversible, and we generally don't get a stable alcohol product. Now, in general, the ketone form is favored when you have alkoxide, hydroxide, halide, or sulfate nucleophiles. Generally, the parent ketone is favored under acid catalyzed conditions and base catalyzed conditions for that matter. The carbonyl carbon-oxygen bond is relatively stable. Does this idea make sense? Okay. So one important sort of intermediate or one important relative of the hydrate is the acetal and hemiacetal. So an acetal is an organic compound formed by the condensation of 2 alcohol molecules with an aldehyde or ketone. And if it's formed from a ketone, we call it a ketol. A hemiacetal, hemi meaning half, is an intermediate formed from the condensation of a single alcohol molecule with an aldehyde or ketone. So we have hemiacetals, hemi, they have one hydroxyl substituent and one alkoxy substituent, while acetals have incorporated 2 alkoxy substituents. Does everyone understand the distinction between an acetal and a hemiacetal? Does this make sense to everyone? Now, hemiacetal and acetal formation is reversible, with one very important exception. Cyclic acetals are isolable and easily prepared under acidic conditions. And part of the reason for that stems from the fact that you get an intermediate where your second equivalent of alcohol, your second nucleophile, is attacking via an intramolecular addition. Now, the main benefit of having these tethered cyclic acetals is that they are much more difficult to hydrolyze, and the equilibrium generally favors the acetal form because the second attack, where you're closing this cyclic acetal ring and you're making your desired cyclic acetal, is intramolecular. And that makes this process substantially faster, and it makes the equilibrium substantially more favored for this cyclic product. Does everyone see how once our first alcohol motif adds in, our second alcohol is now tethered, and as a result, the second attack to go from this hemiacetal to the desired acetal product is intramolecular. And as we've talked about time and time again, intramolecular reactions are faster and they're way easier kinetically to occur. Intra, within the same molecule. So we have our nucleophile, we have our second equivalent of alcohol in the same molecule. While in inter, we would be taking a ketone and we'd be forcefully trying to add 2 equivalents of our alcohol. So this would be an example of an intermolecular process. And generally, intramolecular reactions are way faster. And because both of our alcohol equivalents are tethered when we're making a cyclic acetal, it's much more difficult to hydrolyze off this cyclic acetal. And it makes these cyclic acetals quite stable. Does that point make sense to everyone? Any other questions on this idea? Now, where is this useful? Well, acetals are a useful protecting group for ketones and aldehydes, and the ketone or aldehyde can be deprotected under aqueous acidic conditions. So this is another case where we learned of a new protecting group, this time a useful protecting group to mask a carbonyl. To show you an example of where this can come into play, suppose we have this cyclic acetal and we have an alcohol. Okay. So if we treat this with PCC and oxidize our alcohol, that gives us a ketone. Our other ketone is still protected, so we can take this ketone and carry it forward, and we can do, for example, a Grignard addition. That in turn would give us our addition product. And then from there, we can treat with acid, and that gives us a highly substituted alpha hydroxy ketone. So does everyone see how, because cyclic acetals can serve as protecting group for ketones, we can mask its reactivity and complete reactions that otherwise wouldn't be possible under this current sequence? Does that make sense to everyone? Does everyone see the utility of these cyclic acetals as protecting groups? Perfect.
When you did the Grignard reaction, is that H3O?
Yeah, H3O plus. Yeah. Just in the second step, of course, because if we mix a Grignard and acid, we would just get nothing productive happening. Okay, so let's talk about the two mechanisms to make hemiacetals. The first of which is the neutral pathway. So in this case, we have our alcohol. It attacks our carbonyl carbon. And then from there, we have a series of proton transfer steps. So we pull off a proton from our added alkoxy group, and then we protonate our alkoxide ion generated. That in turn gives us our hemiacetal. Or we can use the acid catalyzed pathway, which is very similar to the pathway for hydration. So in the first step, to activate our carbonyl carbon, we protonate our carbonyl oxygen. From there, we have a much more activated electrophilic carbonyl carbon that our nucleophilic alcohol can attack. From here, all we have to do is remove a proton, and that gives us our desired hemiacetal. The acid catalyzed pathway for hemiacetal formation is generally faster, and that's why we often prepare acetals and hemiacetals under acid catalyzed conditions.
Do you mind scrolling down a little bit, Professor?
Up or down?
There you go. Thank you.
Okay, perfect. Okay, so how do we get to an acetal? Well, under acidic conditions, generally the only way to easily generate an acetal is under acidic conditions. So just like before for our hemiacetal conditions, we're going to protonate our carbonyl oxygen. We have a much more electrophilic carbonyl carbon now. We can attack our electrophilic carbonyl carbon, and after a proton transfer, rather than just deprotonating to get the hemiacetal, we're going to do a series of proton transfers to activate this alcohol as a leaving group. So hydroxide, not a good leaving group. Water is a wonderful leaving group. So what we're going to do is we're going to protonate our alcohol and activate it as a leaving group. So now that we've activated water as a leaving group, now that we have a good leaving group, we can kick out water and regenerate a carbonyl. However, this carbonyl is not very stable because it's an oxonium ion. So it can be readily attacked with nucleophiles. And if we have a lot of alcohol floating around, our alcohol will readily attack the very electrophilic oxonium ion carbon. From here, all we have to do is one more deprotonation step, and we've gotten to our desired acetal product. Does this mechanism make sense to everyone?
Where is the arrow going from the double bonded oxygen? Is it going to?
To the oxygen. Yeah, just to be clear on that, it's going to the oxygen.
Okay.
Does that make sense?
Yes.
Perfect. Any questions on this mechanism for acetal formation? Generally, the only easy way to make acetals are under mildly acidic conditions. Okay. So let's try to apply what we've learned here, and I'd like you to predict the product from each step of the following reaction sequence and draw a mechanism for the following reaction. So I have an intermediate. Intermediates are commonly drawn in brackets. In this case, if we have ethanol and we're under acidic conditions, what are we going to make from our ketone? If we treat a ketone with an alcohol under acidic conditions, what are we going to make? We're going to make two products. One is an intermediate and one is our final product. What are these conditions going to accomplish?
Is it an acetal?
Yep, we're going to make an acetal. Yep.
And then a hemiacetal in the intermediate?
Exactly right. So let's take the next 3 to 4 minutes and let's try to draw an arrow pushing mechanism for this reaction, noting that we're under acidic conditions for how we're going to form an acetal and hemiacetal from this corresponding cyclopentyl ketone and ethanol. So I'd like to see students share their mechanism as either a photo in the chat or to annotate their mechanism directly on the class whiteboard. I just want to make sure everyone's comfortable with the full step-by-step arrow pushing mechanism for this reaction, because this pattern of carbonyl addition, proton transfer, second addition shows up a lot in later mechanisms involving carbonyl chemistry.
So would we protonate the ketone first?
Yep, exactly right. If we're under acidic conditions, we'd start with protonation to activate our ketone. Now, what would happen next? Now that we have this super activated electrophilic carbonyl carbon, what is going to attack?
The alcohol.
Okay. So in this case, our alcohol is ethanol, and it will attack our electrophilic carbonyl carbon. Now, we're not quite done. What's our cleanup step to get our hemiacetal?
Depronate the ether.
Yep. Or yeah, that's one way to view it. Yeah. So you deprotonate your ether, and that generates our desired hemiacetal. Yep, perfect. So we have our hemiacetal. So where do we go from here? So we have our hemiacetal. So how do we go all the way to the acetal? What's our next step?
Is it the 1,2 addition?
So there's no carbonyl yet, or no oxonium ion yet. So
Oh,
in order to
sorry.
get a carbonyl, we eventually want to replace this hydroxyl group with an alkoxy group.
Is it a 1,2 elimination then?
Yep, but before we eliminate, if we're under acidic conditions, how do we activate hydroxide as a leaving group?
Add another proton.
Yep, exactly right. We protonate it to make water. And then we can easily eliminate water to generate and regenerate our carbon-oxygen double bond. So now that we have water, and this is a much better leaving group than what we started with, we can easily kick out water and make our oxonium ion. Okay, we now have this super activated electrophilic position. So what's going to happen next?
Will the alcohol attack it again? Oh, sorry.
Yep, exactly right. So our alcohol, which in this case ethanol, attacks again. And now from here, we're just one step away. We're just one step away from our desired product. And what's our last cleanup step?
Deprotonation.
Yep, exactly right. So water or another reasonably basic species in solution, such as solvent, will pull off our last proton, and that in turn gives us our acetal. Does this mechanism make sense to everyone? Perfect. Any other questions on this topic before we archive today's recording? We're at a good stopping point for today. Any other questions I can address? So with this, we'll archive today's recording.